Good afternoon, everyone. Thanks for sticking around at the end of what I'm sure has been a very long day. And thank you also for allowing me to speak here today. So my name is Shannon Whitlock. I'm a scientific advisor and co-founder of the company QPerfect. So we're a young quantum computing startup out of Strasbourg in France. And so, as you know, you've heard this week, we're at a very exciting moment, I think, in computing, where we're just starting to get access to machines which can perform computations testing the limits of the best classical computers. And I think this is perhaps one of the biggest opportunities we have in the 21st century, promising to unlock numerous applications from, for example, quantum chemistry, drug design, material discovery, optimization, AI, among many other applications. But how close are we really? Quantum computers are still quite limited, both in terms of the number of qubits you have available and also in terms of the effects of noise and gate errors, which makes it very difficult to assess their applicability and precludes many important applications. So to give you an idea of where we're at today, about 2 years ago, IBM announced what's called the 100 by 100 challenge. And the idea was that by today, we should be able to run quantum algorithms with 100 qubits or more and depth of 100 in less than a day. And this really would be an amazing achievement. So this should, in principle, mark the point where quantum computers can finally perform tasks which are impossible to perform even on the biggest supercomputers that we have today. But how do we know if there are not, for example, more efficient classical implementations that could potentially do the same task? So that's why I'm here today. I'm actually here to show you that at QPerfect, we can run complex algorithms like this with nearly 100% accuracy already today. And so as a specific example, I show you this circuit. It's a 100 qubit circuit with a depth of 995, so almost 10 times deeper than the IBM challenge. And it represents a quantum neural network, so a quantum version of a classical neural network, which we hope will speed up all kinds of machine learning tasks, ranging from image recognition, financial modeling, optimization, and so on. And so this is a really complex algorithm. It consists of more than 30,000 gates, 20,000 2-qubit gates. It makes use of very high entanglement. And I don't expect you to be able to verify this right now, but already today, on our platform, Mimik, we can run this circuit and obtain measurement results. Here's a histogram of sample results corresponding to about 100,000 samples on our platform Mimik. And we obtain this not in days, but in minutes, not on quantum computers, but on a classical computer worth a few $1,000s. And so that's what I want to show you today, how we do this. So at QPerfect, our mission is to make quantum computers work, to work for you. So we enable researchers, developers, manufacturers to realize the full potential of quantum computers. And our goal is to help you unlock industry-transforming applications for the first time. We bring about 30 years experience in quantum computing and advanced numerical simulation of complex quantum systems. And I would say the core of our expertise is at the interface between classical and quantum computing, which, as we've heard this week, is particularly important now with this shift towards hybrid computing, HPC, AI, and quantum. And as our first effort, we've developed a quantum emulator, so a classical computer that can simulate quantum computers at a scale which is actually interesting and relevant for applications. And so that's what I want to share with you today. But maybe before I start, let me do a quick survey, so with a quick show of hands. How many of you are working in quantum algorithm design or use case development? Okay, not many. How many of you are working in quantum hardware development or perhaps developing platforms in order to provide quantum services? A few, very good. So I think all of you need to have the best emulation tools for you and for your customers in order to improve productivity, to test algorithms, and to get the edge over your competition. So that's why I'm particularly proud here today to announce the release of our first product, Mimik, the world's most powerful virtual quantum computer. So whether you're a hardware developer, a software developer, a service provider, or simply end user, Mimik has all the features to accelerate your quantum journey. So Mimik is a cloud-based, fully universal quantum computing platform that allows you already today to program and run quantum circuits with thousands of qubits and millions of gates at or exceeding the performance of today's quantum computers. It incorporates industry-leading simulation engines, including our own highly optimized state vector simulator, a proprietary tensor network simulator. It provides access to more computing resources over the cloud. It's very easy to use with, for example, Python and Julia APIs, large library of circuit primitives for building complex quantum algorithms, open QASM support. Plus, it allows you to do something you cannot even do on a quantum computer. So with Mimik, you can access, for example, full state properties of the system, including fidelity estimates, state vector amplitudes, expectation values, and entanglement measures. So how does this work? As you know, simulating quantum computers on classical ones is a notoriously difficult problem. So if I was to try and represent the full quantum state of n qubits in a classical memory, I would have to somehow store 2 to the power n complex numbers. So with 32 qubits, you can do this with a regular PC. 40 qubits, you start to require a small-scale HPC, maybe a little bit like the Fujitsu quantum computer simulator. And 50 qubits would require more memory than is available on the world's biggest supercomputers. At QPerfect, we get around this using matrix product states. So this is a tensor network method which has been developed by the many-body physics community over the last couple of decades. And what it does is allows you to represent the quantum state in a highly compressed form, in the form of what's called a matrix product. So it's a chain of matrices, and each of these matrices can be compressed, in many cases providing a representation of the quantum state, which is orders of magnitude smaller than, let's say, the full state vector representation. And this is an extremely powerful technique for simulating quantum computers, because many quantum algorithms that are in use today, they have a lot of structure, and in fact, they don't even use the full state space. And so you can really test quantum algorithms at a scale that perhaps before was unthinkable, so beyond 50, hundreds of qubits. And so this has become now, I would say, the gold standard for simulating and benchmarking quantum computers with 50 plus qubits. But let me just stress, not all MPS simulators are equal. So we took a lot of care and relied on our deep expertise in simulating complex systems to build Mimik from the ground up in a way that provides almost optimal representations, not only of the quantum state, but also of the quantum circuit that you're trying to evaluate. And what this does is provides speed and accuracy far beyond other simulators and allows you to solve problems which are impossible to solve on any other platform. So we are already providing value to our users today. Mimik can be used, for example, for designing new quantum algorithms, both variational quantum algorithms and fault-tolerant ones, digital twins, including realistic constraints of hardware platforms and noise models. It can be used for benchmarking quantum computers at the limits of what's possible with classical computers. It can be used for quantum-inspired algorithms, which could provide some kind of business value even without the use of quantum computers. And it can be used to advance the development of the next generation quantum computers and quantum error correction schemes. Before I go on, let me just share with you maybe a small anecdote from one of our early testers. So this is an individual who I won't name, but he identifies himself as the least qualified person in quantum. He's actually tested a very large number of different quantum platforms and has a special talent for finding their breaking points. So he approached Mimik with a mix of curiosity and skepticism as to our claims. So he started off with some standard benchmark circuits. I think it was quantum phase estimation and the HHL algorithm with around 20 qubits. Immediately, he was impressed with the speed of Mimik compared to his own local state vector simulators. Encouraged, he moved on to a bigger problem. So he brought a 100 plus qubit circuit, which I think was from a quantum chemistry problem, and Mimik solved it in a matter of seconds. Then he admitted to me that he had no way of verifying the results because he had never been able to simulate or solve this circuit on any other platform. Undeterred, he came back a week later with some new circuits, which included a swap test, which would allow him to verify the sample results, including a massive circuit of more than 1,400 qubits. Mimik solved it and gave accurate results within just 6 minutes. So his conclusion, Mimik should be possible to execute any quantum circuit that can be run on a quantum computer today, including those that are not publicly available. And Mimik is fast, accurate, and in a league of its own. So here's some benchmarking results that shows the speed of Mimik over some other simulator platforms. So at the top you see Mimik and 2 other commonly used simulators. And from the left to right, you see 3 different algorithms consisting of 8 qubits, 12 qubits, and 16 qubits. So Mimik has been meticulously optimized from the ground level, making use of low-level CPU optimizations and memory optimizations to achieve the best possible simulation speed. So what you see in the graph is the time to solution, including the open chasm importing, executing the circuit, and sampling 1,000 measurement results. And you see Mimik can solve each of these circuits in a matter of milliseconds, up to 80 times faster than other alternatives. But Mimik is not just fast, it's also full of features. So think of it as the Lexus of quantum emulators, if you like. So this is typical performance that we see up to around 20-25 qubits. Above that, Mimik automatically switches over to a highly optimized MPS simulator engine, which provides even more performance gains and allows you to solve problems which are impossible to solve with any other technique. So we've tested Mimik on a very large number of benchmark circuits, and I display some of our results here. So these are obtained using one of the largest public benchmark suites, which was published by Munich Quantum Toolkit. It consists of over 70,000 quantum circuits, covering 28 commonly used algorithms, with between 2 and 130 qubits each. So on the left, you see the benchmark circuit that I presented at the very beginning, the quantum neural network. And the circle here represents the fraction of circuits that we can solve exactly, without error, on Mimik within a 30-minute runtime. In this case, we could run 100% of these circuits all the way up to the maximum size provided in the benchmark library, which was 130 qubits. On the right-hand side, you see a selection of other algorithms that we have tested, including common circuit primitives like the quantum Fourier transform, quantum phase estimation, random circuits, as well as full algorithms like Shor's algorithm, QAOA for portfolio optimization, Grover's algorithm, and so on. What's remarkable is that Mimik can solve almost all of these benchmark circuits with 100% accuracy up to the full scale provided by the benchmark library. And we've tested a number of different simulators. None of them even come close to this kind of performance. So at QPerfect, we're pushing the boundaries of what's possible to simulate on classical computers. But that's not all bad for quantum computing, because we also strongly believe that simulation is the key to faster and better development of next-generation quantum computers. And I'm particularly happy here today to present a collaboration that we started recently with Quera Computing, you heard from earlier, which is aimed at propelling large-scale simulations of error-corrected quantum algorithms for improving their architectures towards fault tolerance. Mimik is the only platform capable of simulating hundreds of physical qubits necessary to test real error-correcting quantum algorithms without any restriction over the types of gates or operations that you use. And so this is particularly important when assessing the impact of realistic noise or perhaps new quantum error-correcting codes beyond the usual stabilizer type codes. But also you can use Mimik to test now full logical circuits. And so as part of this collaboration, our target was to simulate a particular circuit, this magic state distillation circuit, which was particularly challenging, I would say. It's a circuit which consists of 16 logical qubits, each logical qubit dozens of physical qubits, not even counting the ancillars, so more than 270 physical qubits. It includes non-Clifford gates, T-state injection, plus all of the machinery for doing the quantum error correction cycles. So the measurements, the feedback, the decoding, and so on. So at the beginning, it wasn't clear that we could simulate this at all. No one has simulated such a circuit. Now, after some effort, we get this down to a few minutes. So this now opens up the possibility to test quantum error correction codes, fault-tolerant quantum circuits at a scale, including, for example, realistic constraints of the hardware. So with that, I'm going to conclude. Whether you're a hardware developer, software developer, or you simply need a simulation partner, QPerfect is here to help. We are the leaders in quantum emulation. We're relentless in solving problems, and we want to work with you. So in fact, as a special offer here at Q2B, we invite you to connect to us on LinkedIn, send us your circuits, and we'll simulate them on Mimik for you and share you the results. I guarantee you won't be disappointed. Otherwise, you can immediately access Mimik. It's available now. We have subscription plans, so you can get started right away. Or if you're operating, for example, HPC infrastructure, or if you want an on-premise, we also can design custom solutions for you. So with that, from me and on behalf of the whole team at QPerfect, thank you for your attention.